In C and C++, undefined behavior is a structural contract. It is a license that allows the compiler to assume certain states will never occur, generating highly optimized machine code. If a programmer breaks that contract by letting an integer overflow or a pointer drift past its allocated memory, the compiler's assumptions collapse. Because the compiler assumed this illegal state was impossible, it generates no contingency instructions, which leads directly to memory corruption vulnerabilities. To address these outcomes, the C11 language standard introduced the Analyzability Annex. This revision categorizes and contains these execution paths, separating wild execution from manageable errors. This split-screen visualization shows how C11 redefines these failures. On the left is critical undefined behavior, where an overflow is allowed to bleed outward and corrupt adjacent memory. On the right is bounded undefined behavior, where a structural barrier contains the failure and traps the execution. Under this annex, the compiler guarantees bounded undefined behavior never writes outside an object's precise bounds. The program may halt, but won't secretly corrupt system state. Language standards, however, are theoretical documents. A paper mandate cannot physically stop a CPU from executing a malformed instruction sequence. Enforcing these boundaries requires mechanical intervention at compile time. This is the role of Clang's UndefinedBehaviorSanitizer, or UBSan. UBSan does not parse high-level C syntax to look for bugs. Instead, it operates within the compilation pipeline, physically mutating the binary at the LLVM intermediate representation stage. By injecting raw checks into the intermediate code, UBSan changes the size, the instruction layout, and the final execution speed. Securing C and C++ requires translating theoretical safety standards into hard LLVM intermediate representation, imposing specific changes on the final binary architecture. Compiled with the -f sanitize equals undefined flag, the compiler physically injects safety barriers into LLVM IR. A standard addition instruction is followed by an ICMP instruction for range verification. If the check fails, a conditional branch redirects execution to an external callback named _UBSan handle mul overflow. Processing that callback requires the binary to link against a runtime library, libclangrt.ubsan. This library formats and prints the verbose diagnostic error messages engineers see in their terminal. There is a hidden cost to this structure. Because the instrumented function now contains a call to an external runtime library, the compiler can no longer treat it as a leaf function. It must spill caller-saved registers to the stack before the check and reload them afterward. In bare metal environments or operating system kernels, this degree of register disruption and stack bloat is unacceptable. Space and memory access times are strictly limited. The first mitigation tier is the -f sanitize minimal runtime flag. This strips out the verbose diagnostic arguments, which shrinks the footprint of the callback and reduces the binary size. A 2025 toolchain update improved this further by applying the preserve all calling convention to these minimal runtime callbacks on x86-64 and AArch64 systems. The preserve all convention dictates that the callback itself must preserve the state of every register. This removes the need for the compiler to spill and reload caller-saved registers around every bounds check in the main program. Even with register spilling solved and a minimal runtime in place, forcing the CPU to branch out to an external callback alters the primary execution flow. Any callback structure alters highly constrained kernel-level execution states, necessitating strategies that function without an external runtime. Highly constrained execution spaces operate under strict requirements. They cannot rely on external diagnostic libraries to handle memory faults. To meet this constraint, compilers offer trap mode. By omitting the LLVM.UBSan trap intrinsic, engineers completely eliminate the runtime library dependency. Instead of branching to an external logging function, trap mode resolves the error locally with a direct hardware-level trap instruction that terminates the process. This flowchart details how the intrinsic translates to silicon. On x86-64, LLVM.UBSan trap lowers to a 4-byte UD1 instruction. On Arch64, it lowers to a 16-bit BRK immediate. Both architectures embed the UBSan integer error code, leaving a fingerprint of the failure type inside the trap. Without a diagnostic library, custom OS signal handlers are deployed to step in at runtime. They disassemble the instruction address where the trap occurred and extract that embedded integer to identify the failure type. This solution encounters hardware limitations when ported to alternative architectures, most notably PowerPC. The PowerPC instruction set uses a specific encoding format for its traps. When configured as an unconditional trap, the available encoding space collapses. This leaves only 4 usable bits in the instruction structure. 4 bits can only represent 16 distinct states, which is insufficient to carry the full spectrum of modern UBSan error codes. Implementing zero runtime security shifts the performance bottleneck away from compiler software and places it onto the physical constraints of the CPU's instruction set. Even when hardware traps are perfectly encoded, they carry an execution penalty inside optimized code paths. Modern CPUs rely on aggressive instruction pipelining. The presence of a hardware trap instruction forces the processor to prepare for a context switch, which disrupts efficiency even when the trap is never taken. To bypass these pipeline penalties, a 2026 compiler update introduced loop mode, driven by the llvm.looptrap intrinsic. Instead of emitting a trap, the compiler lowers the llvm.looptrap intrinsic into a short conditional branch instruction during the late optimization passes. This timeline illustrates how this operates on an x86 system. The compiler outputs a 2-byte branch instruction that branches directly backward to its own address, creating an infinite loop. Data on modern AMD and Intel microarchitectures prove that the CPU processes an untaken conditional branch faster than an untaken hardware trap, preserving the integrity of the instruction pipeline. Triggering this loop creates an operational problem. Instead of crashing the program, the process is frozen in a spin state, consuming a CPU cycle endlessly. To manage this, systems engineers must pair loop mode with external watchdogs or interrupt handlers. These external systems are tasked with detecting the frozen spin state and terminating the thread. This represents a distinct design choice. Loop mode sacrifices the immediate introspection of trap mode in exchange for raw pipeline speed during normal execution. Modern compiler instrumentation is forced to adapt to the physical branch prediction habits of raw silicon to satisfy language specifications. This scatter plot maps the C++ security trade-off, weighing diagnostic detail on the y-axis against performance efficiency on the x-axis. Default mode provides high detail but low performance due to code bloat. Conversely, trap and loop modes deliver high performance but almost zero diagnostic detail. To break this trade-off matrix, selective UBSan uses execution data to prioritize instrumentation. This relies on profile-guided optimization. During preliminary runs of the software, the compiler records the execution frequencies, mapping pathways handling the most traffic. Engineers then apply the -f sanitize skip hot cutoff flag. This parameter defines a cumulative mass percentile that acts as a limit for instrumenting high-traffic code. Armed with this profile data, the compiler actively strips the security checks from the hottest execution paths. The data flows unobstructed where speed is critical. This approach secures the majority of cold code where rare edge cases occur, while leaving the critical fraction of hot path instructions optimized for speed. Undefined behavior allows C and C++ to reach high performance levels by stripping safety checks from the instruction stream. By combining C11 categorizations with physical LLVM-IR manipulation, modern tooling gives engineers control over the balance between software safety and hardware efficiency.